Welcome back to Pentagramprime, everyone. Today we will be looking at the definite integral of cosine of 4 theta divided by 2 plus cosine theta from 0 to 2 pi. Exercise number 23 on page 303 of Marsden and Hoffman suggests that we look at the integral of e to the 4I theta divided by 2 plus cosine of theta about the unit circle along the same domain and consider its real component in order to solve the aforementioned real integral. So, for the purposes of record keeping, we will refer to the integral of cosine of 4 theta divided by 2 plus cosine theta, the integral that we are tasked with solving, as I1. The other integral, the one with e to the 4I theta in the numerator, will be referred to as I2. The path of integration for I2 makes it convenient for us to convert it to an integral in the complex plane along the unit circle. We do this via the change of variable z equals e to the I theta. This conversion changes e to the 4I theta in the numerator into z to the 4th. The same change of variable, along with Euler's relation as shown on page 270, changes cosine of theta into z plus 1 over z quantity divided by 2, and oh yes, we are no longer dealing with an integral over a domain for theta. We are dealing with a closed loop along the unit circle in the complex plane that will be referred to as lowercase gamma. The factor of I in the denominator becomes negative I in the numerator, and we factor out a 2 from the denominator, which gives us minus 2iz to the 4th in the numerator. Combining z in the denominator with 4 plus z plus 1 over z leaves us with a second-order polynomial in the denominator to tell us where the singularities are in the complex plane. I should note that the substitution we perform does by itself constitute a removable singularity at z equals 0. However, the residue of the integrand is 0 at the origin because the residue of any removable singularity is 0. So, it does not affect the final answer and will be ignored going forward in this example. For bookkeeping purposes, I'm going to pause here and define the integrand of I2 as the function f2, mostly because we'll momentarily be focusing more on the integrand than on the integral overall. Also, I keep worrying that I'm going to mispronounce integrand. Application of quadratic formula to the denominator of f2 indicates singularities at z equals negative 2 plus or minus root 3. Factoring the polynomial indicates simple poles at both of these locations. Plotting these points in the complex plane indicates that negative 2 plus root 3 is the only singularity that lies inside of the path of integration given by the unit circle. Residue theorem, described on page 256, tells us that the integral shown here equals 2 pi I times the sum of the residues of the singularities located inside of the closed loop being integrated upon. In our case, it's the unit circle. Since there is only one singularity meeting this criteria, the expression referenced on page 256, along with the integral I2, becomes the residue of f2 at z equals negative 2 plus root 3, and its winding number, referenced on page 256, becomes 1 because we are assuming a counterclockwise path about the unit circle. In order to determine which method to use for calculation of the residue, we will separate f2 into functions g and h for the numerator and denominator respectively. We will momentarily be using the original form of the denominator of f2 since it is easier to work with. Upon taking the derivative of h and evaluating it at minus 2 plus root 3, we see that it is non-zero at the singularity. Evaluating h and g at z equals negative 2 plus root 3, we see that h is 0 and g has a non-zero value in the singularity. The three values of h prime, h, and g show us that the singularity in f2 at z equals minus 2 plus root 3 meets the requirements for use of proposition 412 on page 244 as a means of evaluating the residue in question. There is a link to episode 60 in the description, which covers its use. Inserting the values for g and h prime into the residue formula listed in proposition 412, we get minus 2I times 97 minus 56 root 3 on top of 2 root 3 in the denominator. 2's cancel, and we can simplify matters by multiplying top and bottom by root 3. This leaves us with minus I times 97 root 3 minus 168 quantity over 3. Inserting our value for the residue at z equals minus 2 plus root 3 and carrying out the multiplication with 2 pi I, we see that the i's combine to become negative 1, and we have a value of I2 that is equal to a real number. Even though I2 is real, we will express it in complex form using a plus ib notation for reasons that will become apparent momentarily. The imaginary component is, of course, 0. If we take the original form of I2 and use Euler's relation to convert e to the 4I theta into cosine of 4 theta plus I sine of 4 theta, then we can split the integral into real and imaginary components. Placing this expression alongside the solution that we just calculated for I2, we see that the imaginary portion of the integral, sine of 4 theta divided by 2 plus cosine of theta, is equal to 0, and the real portion of the integral that we just calculated is equal to cosine of 4 theta divided by 2 plus cosine theta. So, by comparison to I2, we now have a value for the definite integral I1. I am, as always, at your disposal in the space below this video. Till next time, this is Pentagram Prime signing off.